Good morning, students. Now we will discuss electric flux density. Electric flux density. It is denoted as d bar. It is represented as d bar. First, we will discuss the definition for this electric flux density, and after that, the relation between electric flux density d bar and electric field intensity E bar. Those are the 2 points we will observe right now. First thing here, electric flux density. It is defined as the amount of flux lines passing normal through unit surface area. It is called as electric flux density. The amount of flux lines, the amount of flux lines passing normal. Here normal means perpendicular to the plane. For example, if we're having a plane like this paper, now normal means like this. This is the normal. That means we are placing perpendicular to the paper through unit surface area. That is called as electric flux density. It is defined as the amount of flux lines passing normal through unit surface area, and it is represented as d bar. Simply, d bar can be written as d bar equal to psi by s. Here psi is nothing but the amount of flux lines. S is nothing but unit surface area. The amount of flux lines, and S is nothing but unit surface area. Here it is the amount of flux lines. It is unit surface area. And the units for this d bar is, for this one, coulombs. For surface area, units are meter square. So the units for d bar is coulombs per meter square. For example, when a charged particle is placed like this is the charged particle. Now this charged particle creates a field around it like this. It is the field around the charged particle with a radius of r. R is the radius. And in practical manner, when we see this, it will form a sphere. Here it is the surface area. Now surface area of this sphere is 4 pi r square. Surface area of this sphere is 4 pi r square. Then when we substitute here, and at the same time here a charged particle, we are placing here a charged particle of charge q. Q is the charged particle. That means the amount of flux lines will be originates from this q. So here q equal to psi. Then d bar equal to, instead of this psi, I am substituting q by, instead of this s, I am substituting 4 pi r square. Q by 4 pi r square. Here it is a vector. So it is a magnitude, and the direction can be represented as AR bar, unit vector AR bar. So d bar equal to q by 4 pi r square AR bar. It is the expression for electric flux density d bar. Electric flux density d bar. Now we'll observe the relation between d bar and E bar. Electric field intensity E bar, electric flux density d bar. Here E bar is electric field intensity, d bar is electric flux density. Electric flux density. Now there is relation between those two we have to observe. And here we already known for E bar. We already derived the expression for E bar. E bar equal to, that is, we know that E bar equal to Q by 4 pi epsilon naught R square into AR bar. That is the expression for E bar. And right now we have derived for D bar. D bar equal to Q by 4 pi R square into AR bar. That is the expression for D bar. Now simply what I am having here is I am substituting, then I am making here E bar by D bar. E bar by D bar. I have some value E bar here and I have some value D bar here. So E bar is Q by 4 pi epsilon naught R square into AR bar by D bar means this one, that is Q by 4 pi R square into AR bar. This one, this one, this one, this one cancel. And finally you are having here E bar equal to, E bar by D bar equal to 1 by epsilon naught. 1 by epsilon naught. Then I am cross multiplying here. Then D bar equal to epsilon naught E bar. D bar equal to epsilon naught E bar. It is the relation between E bar and D bar.